Welcome to Introduction to Ultrasound Guided Regional Anesthesia. In this video, we will review key aspects of ultrasound physics. There will be an explanation of the key ultrasound knobs and controls. We will describe techniques for optimization of image quality and techniques for needle insertion. Here we see a prototypical demonstration of a sound wave. The definition of a sound wave is simply areas of compression and relaxation of particles traveling through space. The distance between two pressure peaks is known as the wavelength. The number of pressure peaks per unit time is known as the frequency. The entire length of the ultrasound pulse is known as the pulse length. Ultrasound is simply high-frequency sound. The upper limit of audible sound is 20,000 Hz or 20 kHz. Common clinical ultrasound frequencies are between 2 to 12 MHz. Inside each transducer are piezoelectric crystals. When exposed to an alternating current, these crystals will vibrate. This vibration will disrupt the particles in the medium that the transducer is in contact with. This physical disruption of particles through space is the definition of a sound wave. The sound wave bounces off of an object and returns towards the transducer. When the sound wave strikes the transducer, the piezoelectric crystals will vibrate once again. This time, however, the crystals will convert the mechanical sound energy back into electrical energy. It's this electrical energy that's fed into the computer system and processed to produce an ultrasound image. The more ultrasound that reflects off of an object, the greater the signal intensity will be. The stronger the signal intensity, then the whiter the image. The weaker the signal intensity, then the darker the image. Whiter images are called hyperechoic, and darker images are called hypoechoic. Black images are known as anechoic images. A very important principle of physics is that reflections of ultrasound occur at areas of interfaces between tissues with different acoustic impedances. Acoustic impedance can be considered the tendency of a tissue to reflect ultrasound. It should be obvious to the viewer that if all tissue reflected ultrasound to the same degree, we would have no useful clinical information, as all tissue would appear as the same shade of gray. These principles are demonstrated in this video, in which a ruptured spleen is diagnosed with ultrasound. Several things are obvious in this video. First, the border between the spleen and the normal parenchyma is easily identified. The demarcation between the normal parenchyma and the hemorrhagic tissue is obvious as well. This is secondary to the fact that ultrasound is reflecting at interfaces that have different acoustic impedances. When we remove the graphics, it is still very easy to see all the important areas of this ruptured spleen. Again, this is because of the great difference in acoustic impedance between the various tissues. The objective of an ultrasound scan is to optimize the amount of ultrasound that actually reflects off of an object and returns to the transducer. This is not always possible, however. Some ultrasound will always travel through an object known as transmission. Some ultrasound will change its direction as it passes through an object. This is known as refraction. It should be noted that refraction is a source of artifact generation. This will be covered in a later video series. An important concept of ultrasound physics is attenuation. As ultrasound travels through a media, it loses energy to the surrounding tissues. This loss of energy is mostly in the form of heat. Loss of signal intensity results in degraded image quality of deeper structures. The higher the frequency of the ultrasound system, the more attenuation will occur. Here is a graphic representation of ultrasound attenuation. Note, the lower frequency 5 MHz transducer attenuates less than the higher frequency 10 MHz transducer. The vertical bars are simply graphic representations of the energy in the ultrasound pulse. The operator can deal with ultrasound attenuation by adjusting the gain button. There is usually an overall gain button. There are also usually TGC dials. TGC stands for time gain compensation. The TGC dials allow the operator to control gain at specified depths. When the gain is turned up, the image becomes whiter. When gain is turned down, the image becomes darker. This is an example of a prototypical TGC dial setup. When the buttons are moved from left to right, the image gets brighter at the specified depths. The top buttons control the more superficial aspect of the ultrasound image, whereas the bottom buttons control the deeper structures. In this simulator, we will now demonstrate the use of the TGC dials in the overall gain button. You can see that the simulated nerves, indicated by the arrows, are very dark. The objective would be to increase the TGC dials that control this aspect of the screen in order to brighten the image. We have now successfully compensated for ultrasound attenuation. Some machines will have simply an overall gain button. This button should be turned to the right in order to increase the image brightness, or turn to the left to decrease the image brightness. It should also be noted that an overall gain button may also exist with the TGC dials. The operator can choose how to use each dial independently. Here is an example of how the overall image brightens as we turn the overall gain button towards the right. We have once again compensated for ultrasound attenuation. The next important concept is ultrasound resolution. Resolution refers to the ability to identify objects as independent structures. The higher the resolution, then the better the image detail will be. High-frequency scanning with respect to nerve blocks is considered 10 MHz or greater. There are several different types of resolution, which include axial, lateral, and temporal. The clinical connection of ultrasound resolution is that for superficial blocks such as the interscalene and supraclavicular blocks, high frequencies, 10 to 13 MHz, are utilized to generate the highest resolution and best image. However, because of ultrasound attenuation, lower frequencies, 2 to 8 MHz, are utilized in blocks that require significant tissue penetration, such as neuraxial blocks. From a practical perspective, this means that you may need different probes or settings depending on the type of blocks you commonly perform. The following is an example of a high-frequency scan of a very superficial nerve, the muscocutaneous nerve. You can see intimate detail of this nerve, including fascicles within the nerve. This is characteristic of a high-frequency, high-resolution system. In contrast, the following is an example of a low-frequency scan of a deeper structure, the sciatic nerve. Notice the depth, and also notice how there is less detail with respect to this nerve. The nerve is less distinct. A few facts about frequency. Most ultrasound systems allow the operator to adjust frequencies through a range for a given transducer, such as 8 to 10 MHz. Transducers are generally classified as either high frequency or low frequency. Structures less than 3 centimeters in depth are best imaged with the highest frequency system possible. State-of-the-art ultrasound imaging is currently in 2 dimensions. Therefore, there are 2 standard imaging planes with respect to the target blood vessels and nerves. These are 1, the short axis view, 2, the long axis view. There is other terminology that you may hear. The short axis view is often referred to as the transverse scan or the cross-sectional view. The long axis view is often referred to as the longitudinal view. With respect to imaging the nerves and blood vessels, it is almost always beneficial to image these structures in their short axis. The benefits of short axis imaging include 1. You can follow the circumferential spread of local anesthetic around the target structures, and you can also identify the needle location easier than if you were imaging these structures in their long axis. We will demonstrate some of these principles by returning to our simulator, in which we are imaging a circular structure known as a simulated vein. The simulated vein in short axis appears as a hypoechoic circle indicated by the white arrow. The long axis view of this structure is generated by rotating the transducer 90 degrees in either direction, as demonstrated here. Here is the demonstration of the corresponding ultrasound image, in which the short axis view is transformed into the long axis view. The short axis view allows a circumferential perspective on the target. In this example here, we have a superficial anterior perspective by the skin, a lateral and medial perspective, and a posterior perspective. Here in this example of the long axis view, note that you have lost the circumferential perspective on the target structure. Instead, we simply have a proximal distal perspective and a posterior perspective. There are two common techniques for needle insertion. These are 1, the in-plane technique, and 2, the out-of-plane technique. Each has its own advantages and disadvantages. The in-plane needle insertion technique has the benefit that the operator has the ability to see the long axis view of the needle. This provides the distinct opportunity to see the entire needle. However, this technique is quite challenging given the very thin nature of the ultrasound beam and the subsequent ergonomic challenges of continuously imaging the needle. Here is the demonstration of the in-plane needle insertion technique. This video also demonstrates the in-plane needle insertion technique. Here is the corresponding ultrasound image that goes along with this simulated needle insertion of the in-plane technique. The white arrow indicates the entrance of the needle into the simulated structure. The transducer is manipulated and the entire needle is now visible as indicated by the 3 arrows. Various maneuvers, which we will discuss in the later aspect of this video, optimize image quality. The in-plane needle insertion technique allows the full visualization of the needle, including its tip, as indicated here. The next example is that of a sciatic block in the popliteal fossa using the in-plane needle insertion technique. The technical description of this block would be the short axis imaging of the neurovascular structures in the use of the in-plane needle insertion technique. The needle can be seen entering screen left, indicated by the arrow. The nerve is a hyperechoic structure that is round in nature. Notice how you can follow the full shaft of the needle and appreciate the spread of local anesthetic in a circumferential manner. This is the distinct advantage of imaging the structure in short axis and inserting the needle using an in-plane technique. Notice how you can visualize the spread of the hypoechoic local anesthetic. The needle is repositioned as necessary to generate circumferential spread. It should be noted that the needle image quality will depend on the angle of insertion of the needle with respect to the transducer and ultrasound beam. The following cartoon demonstrates this important principle. A needle is inserted at a roughly 45-degree angle with respect to the ultrasound transducer. Notice in this graphic representation that the ultrasound pulse gets deflected away from the transducer, and since it does not return to the transducer, a poor image quality gets developed. If, however, the needle is inserted at a very flat relationship with respect to the transducer, the needle will act as a strong specular reflector, and the majority of the ultrasound will reflect off of the needle and return towards the transducer, generating a very clear and distinct needle image. We will now demonstrate this in the simulator. Notice how the needle is being inserted at a very, very flat relationship with respect to the transducer. The needle itself is visualized incredibly well, with the sharp tip noted by the arrowhead on the right-hand side of the screen. In contrast, when the needle is inserted at a roughly 45-degree angle with respect to the transducer, the needle image is degraded. It is still seen, but clearly degraded with respect to the first example. Switching now to the out-of-plane technique. This technique has the limitation that only a short-axis view of the needle is generated. The operator, therefore, cannot be sure that the tip is actually being imaged, in contrast to a variable portion of the shaft of the needle. This technique does have the benefit that the needle often has to travel through less tissue to arrive at the target. Here is the example of how to insert the needle using the out-of-plane technique. It should be apparent from this demonstration that the needle will cross the ultrasound beam only once. In the following demonstration, using the simulator, we can see the needle about to enter into the vein. This is indicated by the arrow. The needle has now apparently entered into the vein, indicated by the arrow once again. Note that the view of the needle using the out-of-plane technique is a small dot. An important limitation of the out-of-plane technique is demonstrated in the following video. Using our simulator once again, the needle is inserted using the out-of-plane technique with the objective to insert the needle into the simulated vein. The ultrasound image is similar to the prior example in which the needle is visualized entering into the simulated vein. However, when the transducer is turned 90 degrees to image the vein in its long axis, we discover a problem. The needle has traveled through the back wall of the blood vessel. This was not apparent on the original short-axis view of the simulated blood vessel using the out-of-plane technique. The next area we will discuss is the parts of scanning. These are specific transducer maneuvers that optimize image quality, both of the needle and the nerve. These include 1. Pressure, 2. Alignment, 3. Rotation, and 4. Tilting. We will now demonstrate each one of these maneuvers using our simulator. Here we see rotation, which is a clockwise, counterclockwise move with the transducer. Next, we see pressure, which is a forward movement with the transducer. Alignment can be considered a proximal distal sliding of the transducer. Finally, tilting is demonstrated here. The next two examples will demonstrate how alignment and tilting can impact on image quality. In the following ultrasound image, when the transducer is slid in a proximal fashion towards the operator, the needle becomes easily visualized. Likewise, the operator can tilt the transducer such that the image quality is greatly improved. This is an example of such a maneuver. Here is the tilting, and here is the corresponding ultrasound image. Notice that the needle is unvisualized, then suddenly it is easily visualized. The next topic is that of focusing. Most ultrasound machines allow the operator to focus the ultrasound beam on the area of interest. This focused area represents the narrowest part of the three-dimensional ultrasound beam. Narrow beams produce the best images. For a given frequency, narrow beams result in better resolution. Here's an example of a prototypical unfocused ultrasound beam. This unfocused ultrasound beam has a near field indicated here in yellow and a far field indicated in red. The focal zone indicated by green is the space between the near field and the far field. Notice how the ultrasound beam diverges after the focal zone. Next, we have an example of a prototypical focused ultrasound beam. Once again, the near field is represented by yellow, the far field by red, and the focal zone by green. Note that the focal zone is now the narrowest part of the ultrasound beam. It should be noted that the ultrasound beam can be electronically focused at different depths. This is demonstrated here in this cartoon. We have 3 transducers, and we have 3 different depths at which the focal zone has been placed. It is important to emphasize that it is at this point, the focal zone, where the image quality will be the best. It therefore follows that the objective of the operator is to place the focal zone over the area of interest. It should also be noted that most ultrasound machines allow the operator to have multiple focal zones. Therefore, with the controls on the machine, the operator would place the focal zones over the multiple areas of interest if they exist. In the bottom right-hand aspect of the ultrasound screen are 2 arrows. These indicate the 2 focal zones. In this particular case, the focal zones are placed too deep. Therefore, the objective would be to change the location of the focal zones to a more superficial location over the target structures. The following video example demonstrates how the image quality will improve over the targets of interest when the focal zones are placed in a correct location. The next topic will be that of the frame rate. The frame rate is how quickly an imaging device produces unique consecutive images called frames. High frame rates are critical in cardiac ultrasound. As the frame rate decreases, motion-related events become progressively blurred. In regional anesthesia, such events would include needle advancement and the injection of local anesthesia. It should be noted that the ultrasound transducer sends out a pulse of ultrasound and then has to listen for it to return. This cycle of sending and listening happens thousands and thousands of times, i.e. frames per second. The image usually appears seamless to the naked eye. However, the farther the ultrasound must travel, i.e. the depth, the less frames per second can be generated, and motion-related events can become progressively blurred. The only way to increase your machine's frame rate is to decrease the imaging depth. In this example, we can see that to send a pulse of ultrasound 4 centimeters deep takes a lot longer than sending a pulse of ultrasound 1 centimeter deep. The following video demonstrates the correct depth selection. It should be evident from this video that in addition to improving a machine's frame rate, selecting the appropriate depth also produces the highest quality image that is magnified. The last topic that we will discuss is color Doppler and its applications. This is a very important technology. It is a technology that allows identification of blood flow. It allows the determination of both the directionality and velocity of blood flow. Regional anesthesiologists are simply interested, however, in whether or not there is blood flow rather than the actual quantification of this flow. It is standard to screen the anticipated trajectory of the needle with color Doppler in order to identify any unsuspected vascularity. The following cartoon demonstrates the Doppler principle. In the top aspect of this cartoon, we have a pulse of ultrasound that is traveling towards red blood cells that are moving away from the transducer. When this ultrasound pulse bounces off of the red blood cells and returns towards the transducer, the frequency is now smaller. The bottom aspect of the cartoon, we see that when a pulse of ultrasound strikes red blood cells that are moving towards the transducer, the reflected returning frequency is larger. These principles are demonstrated in this video. There is an ultrasound pulse that is generated. It travels towards red blood cells moving away. The returning frequency is smaller. Here, when the ultrasound bounces off of the red blood cells moving towards the transducer, we have a higher frequency returning. Here is the Doppler equation. FD stands for the frequency shift that is noted in the returning pulse. Ft is a transmitted frequency. C is the velocity of blood in tissue. This is a constant and is usually considered to be 1,540 meters per second. V is the velocity for blood, which normally the machine is solving for. Cosine of theta is equal to the cosine of the angle between the blood flow and the ultrasound beam. This will be addressed in more detail in the next section. So from this equation, it is obvious that there are two pieces of information that can be gleaned from the Doppler equation. One is the directionality of the blood, either moving away or towards the transducer, and two, the velocity. The actual quantification of the velocity of blood flow is not of interest to the regional anesthesiologist. Our objective is to simply identify if there is or is not blood flow. The following example demonstrates why this equation really matters from a clinical perspective. Here we see the carotid artery and internal jugular vein. However, it appears that there is no flow within the internal jugular vein. It turns out that the Doppler equation mandates that the angle between the blood flow and the ultrasound beam be at 0 degrees. However, often in regional anesthesia applications, the relationship between the blood flow and the ultrasound beam is 90 degrees. When this happens, the cosine of 90 degrees is 0. This generates the artifactual no-flow situation. All the operator has to do is tilt the transducer such that there is at least a 10-degree relationship between the ultrasound beam and the blood flow. This then will indicate blood flow if it exists. We see that after a slight tilt of the transducer, there is now blood flow easily demonstrated in this blood vessel. The relationship between blood flow and the ultrasound beam is now not 90 degrees. In summary, there are several principles of ultrasound physics that have actual clinical implications. These include frequency, attenuation, resolution, and the Doppler effect. Most nerves and blood vessels are imaged in short axis. Two standard needle insertion techniques are the in-plane technique and the out-of-plane technique.